R, record, share screen. Here's the latest. Hey,
Okay.
where are my guys? Have you heard from anybody?
Nope.
I haven't heard from Jacob, and I don't know. I haven't heard from James. So
That's an interesting. It formed over land.
yeah, that's because they probably named it more than it's just. It's been warm waters down there under a big ridge, so it's been really bad.
Yeah, it came in as a Cat 4, not Nicaragua, I believe.
Hey Nick, did you send me? You sent me your
homework? Yeah.
Email it to me.
Yeah, I thought I did.
Yeah. No, I think you did. I want to look at yours.
You got mine?
I got yours too. Although you did something.
Yeah,
That was a weird way. I don't want to show people that one. That's
yeah. Okay, well, I kind of figured that.
All right, let's try this mail. But Nick, you did it the way it's supposed to be. You both got the same answer, so again, there's more than one way to skin a cat.
Great minds think alike.
Or differently, but still get the same answer.
That's right.
Oh God, College Duty page switched to Duo Push now.
I love it.
It's great. I had it at Penn State.
I hate it.
Why do you hate it? It's so easy.
Hate it down here.
Oh, I hate it.
Because before they never had it. It was so annoying.
Okay, I need to find Nick. Where are you, Nick?
I should have sent it on Monday.
Yeah, there you are. Okay, the vorticity vector's not correct, but this problem was. So we need to talk about that vorticity vector. So 42 degrees at latitude, writes it down. Longitude conversion. So he's saying 1 degree of longitude, which is good, right? This is important. It's 111, it's the distance, times the cosine of the latitude. So that's important, that you have to know what's the distance that you traveled. So it's 82.489 kilometers. Now, again, I would put stuff into scientific notation and make things better. Rather than kilometers, I'd do it 8.249 times 10 to the 4th meters.
Okay.
Okay. Now, what I like about this is that you wrote the velocity vector. And the first thing you did was you said, all right, well, that's fine. This is 0, because it's moving zonally. Pure zonal motion. Then we go, it's 1 degree longitude. So he said dx dt, 1 degree longitude, times 5 hours. Now, this is a little messy, but it's times 2 because it's 2 hours. No.
Or it's 2 degrees longitude.
It's 2 degrees. Okay, so 2 degrees. And then he said, okay, he's putting the negative sign in here because it's traveling from 92 west to 94 west. So you're traveling to the west, which is a negative velocity. It's to the east is positive. So the way that you figure that, then it's just multiplying, hold on, right? All of this is just multiplying by 1 because 1 hour over 60 minutes is 1, 1 minute over 60 seconds is 1, 1,000 meters over 1 kilometer is 1. The kilometers end up canceling. So I like this perception of how to cancel units. I like that you're using different colors. Nick, these are good things that will serve you right. And then you simply multiply it out and you get negative 9.165 meters per second. Is that what you got, Jim, or did you get 9.18?
Hold on.
I'm a little late. My computer blue screened.
Well,
Didn't know where you were. I was wondering about you. We missed you last week.
I was there on Thursday.
You were here last Thursday?
Yes.
Yeah, I missed last Tuesday's class.
Okay.
I got 9.18.
No, that's what I got. So 9.18. I wonder where. Well, I may have gone 82.5 kilometers. I may have just rounded up.
I would say that would be within the standard deviation.
I think that is going to be more than fine for that. Again, that would force me to have to write this down. You got 1 degree of longitude times cosine of latitude.
Yeah, maybe it was just significant digits eventually.
Oh, I'm looking at the wrong problem. It's probably significant. I'm gonna skip that. I don't want to waste my time with that. Okay, so that's good. So then the other one is the vorticity problem. Okay, and neither of you got that. James, did you send me the stuff you were supposed to?
Which stuff?
You were supposed to send me the solution to these problems.
I probably didn't end up doing that. Yeah, I thought I did, but I'll make sure I've checked that again.
Okay, so you know that you've got to be doing stuff on time. You've got to start making your deadlines.
Yeah.
You know, because right now there's a difference between a student going, I'm really behind, can you give me an extra day? That's fine. It's another time when all of your stuff is always late. That is not good. All right, let us do this with vorticity. And I'm going to do a new screen share on the whiteboard. So I don't have Epic Pen, but I can still do stuff. So the important thing here is that we know that vorticity is del, which is a vector, cross the velocity vector. So we know that del cross V is vorticity. Now, del cross V, in a calculus notation, what do they call that?
The Lagrangian.
Well, no.
Cross product?
Well, it's a cross product, but what do we call del cross V?
A gradient? Is
No, this is called the curl.
Curl.
that what you're getting at?
Yeah, this is a curl.
Oh, curl. Oh my god, I'm stupid.
Okay, so
In my class, we talked about 2 different ways of this. There's like an Eulerian approach and then a Lagrangian approach.
well,
Have you
yeah,
heard of that?
we have that whole lecture in Eulerian and Lagrangian. So
Okay.
we'll be doing more of that as we go into this unit. So
Okay, cool.
not to worry. But when we do that, again, how do we do this? We set up the determinant, right? And we said, all right, we're going to go I hat, J hat, K hat. I'm just reviewing. And this the Laplace, the del operator is just an operator, so it's empty. So it's dx, dy, dv. And velocity is u, j, k. So we take that and we said, first thing we're going to do is we are going to, how do I get the highlighter?
UJK or IJK?
Dude, seriously.
UV.
UVW.
There you go.
Duh. I'm too worried about trying to find my highlighter, which I know
Okay,
is
we'll always fix it for you, Paul.
someplace in here. Where is the highlighter? Maybe spot.
Okay, that's what I got.
Ask Alexa.
Oh, I see what that was. If you can't see my mouse, now you see my mouse, right?
Oh,
You
yeah.
see the red dot, right?
Well, there's
Yeah.
also a red halo there too.
Yeah, that's what I mean. But you don't see the cursor, but I spotlight. Oh, that's awesome. Oh, that's interesting.
Whoa.
Vaca is this way.
I don't know what that is. All right. So, no, I thought there was a. I thought there was a highlighter in here. But I guess not. Well, whatever. So I'm going to do this row, right? And that row, and I'm going to take this stuff. So it's dw dy minus dv dz parentheses I hat. The next one is going to be minus. So I count these rows out, and then I go dw dx minus du dz. And that's going to be in the j hat direction. Zonal, meridional, and then the vertical vorticity, take those ones, is going to be dv dx plus, oh no, minus d
du dy.
dy. So we did this before. So now we've got to figure out, how do we draw this? So in order to draw this, I need to set up a three-dimensional grid system.
Yeah, this is the part that really got me.
Okay, so again, this is your visualization. So do you agree that's the corner of a box? And then I'm going to just call each one of these like a little bit of an arrow, so that I know that they're coordinate systems. Okay. And then what are the axes? What is this axis?
Which one?
This one.
V?
Huh?
V is in Victor?
No, no, no. Axes.
Pi.
This is X.
Oh, I see X, Y, and Z. X, Y, and Z.
Z, right? So this is pointing, again, focus yourself. If this is pointing to the east, then that's the way north would point. So you kind of have to work yourself out. So I have a vorticity vector, and the first one that I have is, and I'm going to use a different color here, is this guy. So it's the vorticity vector has to point in the I direction. So dw dy.
That's a question.
Ask the
That's a
question.
question.
Ask the question.
W, D, Y.
Where's that gonna go?
No, right? I said that's a question. And you need to tell me how that's a question. What is the question? Say that question in English. Allison, go for it.
I'm sorry, can you repeat? My connection went out.
dw dy. That's a question.
The
What is
meridional velocity in the y direction, in the north-south direction.
What's W?
Oh, vertical.
It's a question. So how do you ask the question? How does
the vertical velocity change in the north-south as you go up?
No.
Mm-mm.
As you go to the north-south, from south to north?
But which is positive?
To the north is positive.
Okay, so in other words, see guys, this is one of the things, when I first give all my students that's a question, right? I say, how does W change with respect to Y? Or how does W change as Y changes? That's fine. But the one that's really most important is the third one. How does W change as you go that way? That's really the way you need to think. So W is a vertical velocity, rising air. How does the vertical velocity change as you go that way? Well, which way is that? That's north. So you want to make sure that you use that. So what I'm saying is I'm going to have a vertical velocity that changes and becomes bigger, because that's positive, as I travel to the north. Now, in this case, if I were to put a paddle wheel in here, let me try to draw that a little bit better. Maybe like that. There's the paddle wheel. How will this paddle wheel rotate?
Counterclockwise.
Counterclockwise.
Well, again, I want you to think about, instead of saying counterclockwise, I want you to think about it's rotating that way. So now use your right hand, look against that back wall of the graph system, and curl your right fingers. Which way is your thumb pointing?
Towards me.
Right back at me.
Okay, so
Oh.
it's pointing
Toward
along
the X
the
direction.
x-axis, which makes it the positive vorticity. So
Mm.
when the vertical velocity changes and increases as I travel north, then I've got positive vorticity. Okay, now this one, what is this question here?
How does the meridional velocity change as I go in the vertical?
Okay, but this time I want you to say meridional velocity. What wind? Be specific.
The north to south wind.
Well, no. How does the south wind, because that's a positive V, isn't it? Traveling to the north is positive, so it's a south wind. How does the south wind change as I go up? Because there's a negative sign, I'm saying it gets smaller.
Oh.
So what I'm going to say is that the drawing is this. I'm going to use a slightly different shade of red, because why not? That's a south wind. And as I go north, it becomes less. Won't that arrow cause this thing to rotate? Isn't that just these two darker red arrows? Isn't that going to cause it to rotate like that?
Yes.
You see how that illustrates vorticity. So you have to interpret the derivative correctly. This is saying, how does the southerly wind increase as you go higher? But the answer is it's negative. So the winds going from the south have to become smaller, because a negative change, remember dV/dz is less than 0. A negative is a positive vector pointing in the or in the x direction. Does that make sense?
Okay.
That makes sense, yes. But my question is...
Now do the J hat one. But this is negative. So I think it would be best if I said positive, negative, positive.
Paul, I do have a question. When we're drawing all these out on the grid, do we just draw them like that? Should we do like a new grid for each of them, or
No,
like
we can put them all in one place. So this is going to be
Right.
A hat direction. So it's going to be on this left wall. So the first statement, let's go to the positive one. James, right, what is this statement here?
how does the... I'm really tired in the morning. How does the wind change in relation to height, d/u/dz?
Don't say it that. Don't say in relation to.
As we move further along the z-axis. No.
As we go.
As we go up.
That's better. And what's the U wind?
It's vertical meridional. Use the one that always gets me. I believe it was local wind.
No, zonal.
Zonal.
But that's not the way you'd say it. Nick, how would you say du/dz?
How does the zonal
Not
wind?
zonal. Use directions.
How does the westerly wind change as you go up?
And if it's positive, it means gets
It's
stronger.
increasing.
Okay, so what I want to do here, and I'll use blue, is I draw in a zonal wind. Now keep in mind that this is a west wind, which would be perpendicular or parallel to the x-axis. And I'm going higher, and so I start my vector at the same place, but go higher, like that. And then over here, I'm going to have an ellipse, but it's really a circle. So let me go to here. I'm going to put in a circle that's going to look that way, except I need to, it's kind of squished a little bit, okay? And then how is that circle going to rotate? It's going to rotate on this wall. Now use your hand on that side wall, and then your thumb points in the positive Y direction. Since it's pointing in the Y direction, we would say that's meridional vorticity. Do you see that this is, I mean, in my opinion, this is extremely foundational, but you need to be able to draw, talk, and express, because when you force yourself to do that, you will understand this. Now, on this one, Jim, how about you? Describe this,
Her term,
that term.
the change in velocity with respect to
Which velocity?
the v direction, which is zonal.
I'm looking at W. What is W?
Okay, hold on, which term? Oh, which term are we? I'm sorry, I'm
WDS.
Okay. The W direction, which is the meridional.
No, W is what?
UV. Oh, the vertical.
The vertical wind.
How the vertical wind is changing with respect to the north-south direction.
No.
No.
Look, every time you see this, how does W change with respect to X? W is the vertical wind as I move in the X direction.
Which is to the which is to
the east. So how does the vertical wind change as I move to the east? But in this case, it's supposed to be negative. So the wind, the vertical motion, has to be less as I go to the east. So I have an arrow that points up like this, and I have an arrow that points up like this, and that will cause this circle to spin in a positive direction.
That's actually a lot easier to represent than I was way trying to overcomplicate this when I was working on it. Oh, damn.
Yep.
Right? I mean, this is cool stuff. And so much of this stuff is about visualization. So
yeah.
If I'm really going to visualize something, then what I'd probably want to do is I want to think of this as a tube coming out this way, right? There's a tube here. And I would draw another circle like here. And then I would draw a straight line here. And so what you would see is this tube is rotating this way. The tube is rotating.
Is that how we get our streamwise vorticity, Paul?
Well, yeah, because then we can talk about streamwise and crosswise vorticity, but you can't talk about streamwise and crosswise vorticity until you can visualize it. And then I have an axis in the middle. And if you draw it correctly, you get that axis in the middle. And the vorticity vector is here, pointing in the positive x direction. Now, it's hard because drawing is something that a lot of you aren't very good at. I'm not very good at drawing, but good illustrators see directions and they see where the parallel lines go. But so you have to kind of treat yourself how that's supposed to work. So you get this tube, and the tube is rolling, and the vorticity vector points in the x. Now, I was telling my severe weather class, because, you know, we start doing vorticity with this. I was in San Francisco in the late 90s, and Jerry Straka and Eric Rasmussen, yeah, they were doing vorticity around the updraft of a storm and how the vorticity is, because it's tough to visualize. And you have 200 scientists sitting there with their thumbs pointing in different directions, going all around the updraft, trying to understand what it looked like. Because vorticity requires some visualization. And it is pretty cool. And it is challenging. So there's physical stuff with that. Yeah, the funny thing is this vector, from an artistic perspective, this one is not. Let's go here.
Hello?
Yeah.
Okay, that was really strange, man. Seems like I'll have to try to fix that later. All right. Entire computer just froze up for a second and Zoom crashed.
Oh, it's bad. So there's my vorticity vector. Now, let's do the last one. Let's do now this is obviously vertical vorticity because it's a K-hat. So this is zonal vorticity, meridional vorticity, and this is vertical vorticity.
So I is zonal, J is meridional, and K is vertical.
And we've done that the entire semester. So again, how do you get this? How do you learn stuff better? When you are working it, do you understand that you ought to be talking out loud to yourself so that your vocals start to reflect what your brain is thinking? When you're drawing these pictures, you should be talking out loud. All right, so I've used different colors. Let's use, I guess I could use orange and yellow. I think that'll be fine. So the first thing is, what is this, James?
That is how the meridional wind changes as we go east.
Okay, but what meridional wind?
Oh, dang it. Oh, we literally just called this it. Oh.
Look, that's a south wind.
Oh, the south wind?
V is the south wind. It's from the south.
Okay.
And it gets bigger as I move along the x-axis. Do you agree that those two arrows are now, I mean, again, and part of me just goes, you know what, you need to figure out how to draw these things in 3 dimensions. And I get it, it's not easy. But see, it's a grid, so draw a 3-dimensional grid. So there's the base of it. And then if I have a circle in here, oops. If I have a circle in here, how will that circle rotate?
Oh, counterclockwise. Counterclockwise. There we go.
Okay. And which way would your thumb point?
Towards
Z direction?
In the Z direction, so it's pointing up. So vertical vorticity, positive vertical vorticity points up.
Oh, okay.
Now, if I'm looking down at this, what direction is it? If I look down at this.
Looking at you.
No. If I'm looking down at this thing spinning, this paddle wheel spinning,
Oh, counterclockwise.
Oh,
which is cyclonically.
Yep.
Cyclonic
Cyclonic.
vertical vorticity is positive because it's pointing in the positive or z direction, which is up.
Mhm.
Right? So it is pointing up. So cyclonic rotation is known as positive vorticity. So a lot of people go PVA, they go positive vorticity advection. But really, what's a better way to describe it? Cyclonic. Cyclonic vorticity advection is an upward. Now this one says, sorry, they're still working on all my stairs and they're making loud noises. This one says it is, how does the U wind, which is from the west, change as you travel north, but it's going to get smaller. So I put in here a U wind, which looks this way, and as I go to the north, it spins slower. And that will also cause this to spin positively. So now your job is to label all the colors with the derivative. So what is the yellow?
du over dy.
Not just du dy,
Negative du
Negative
dy.
negative du dy. What is the orange?
Positive
dv.
dv dx.
dv dx. What is the light blue?
That's du
positive,
dz.
negative dw dx.
Right, this is a w, it's a vertical velocity, so that's a negative
Oh,
dw dx. And then what's the dark blue?
Positive
du.
du over dz.
So the dark blue is
oh.
u dz.
Probably help if I labeled the right colors on my diagram a little bit better.
Well, this is something that I would really work at. I would draw this large and really do a beautiful picture. Because remember,
Yeah.
what am I asking you on this final project? The final project is to do all these things. So I expect that this drawing gets redrawn big, large, and perfectly. What's the red?
dw over dy.
And then the dark red?
Negative dv over dz.
And now you understand how vorticity works.
And this is just for all vorticity in general, correct?
This is three-dimensional vorticity. Because
All right.
vorticity is a three-dimensional vector. It is three-dimensional, and the value of this three-dimensional thing is this. It's del cross V.
When we do redraw this, do you want us to show the tube jutting out as you did there?
You could, if you want, if you learned how to draw and you did it something neat. I mean, if you're doing it by hand, you're probably not going to be neat enough, but you could do it. One of the things that I would suggest that you kind of maybe do is, for perspective's sake, is just do something like this.
All right, and while I have
And then when you're here, is to draw yourself squares. Oops. Well, whatever. I'm drawing too neat, too messily. And then you understand how shapes look. That you could actually draw these. You know, you want to draw a bunch of parallel lines in a three-dimensional axis. So then these would go straight up like that, right?
yeah.
So you're kind of creating a three-dimensional grid paper, and then these are all parallel to the x-axis.
And I got one more. I
Yes,
think this
yeah.
is a big question for when I end up doing this, because it's probably going to be on the computer. What was the tool used that you can use to make math notations on Word documents? Because I I
Equation.
sorry, one more time. I didn't hear that.
Equation editor.
I'll write that down really quickly. Editor. I'll be looking that up instead of work
When you
today.
create these little grids here so you can see 3 dimensions, people like me and Jim have it better than you young people, because our first video games, you remember Zaxxon, Jim?
Mm-hmm.
Zaxxon was the beginnings of 3-dimensional rendering, because we had grids that you get perspective by thinking in 3 dimensions. Now they do graphics that are all 3-dimensional based on shading and all this other stuff. This one was a lot simpler, but it was really good from a science perspective to think in 3 dimensions.
I also had a lot of drafting classes in high school, so I had.
Well, exactly, right? That's the first thing I did in college, in engineering, drafting. Engineering graphics. Okay, anyway, does that make sense to you?
Yes.
Okay.
Yeah, absolutely, actually.
I'm going to erase all this because I want to do one more thing here just to show something a little bit different. So I'm going to try to be, as simple as possible. Okay, and I'm going to look at the vorticity this way. And what is this? This is the first term was D. Let me see. I want it to be up here, and that's going to spin it this way, right? So I'm trying to go trying to go fast around here. Okay, and this was the vertical velocity increasing, so dW, as I travel in the y direction. So a good way to test yourself is show vorticity and tell me what the wind, or look at the winds, draw winds and tell me the vorticity from it. But what if I showed you this? And this is where it gets a little mind-blowing. Do you agree that I can spin this Okay. What is this? Do you agree that if I had those pink arrows, so I'm going to do this. I'm going to take the pink arrow. I'm going to take the other arrows off. And I'm just going to look at the pink arrows. Do you agree that's the way it would spin based on the pink arrows?
Yes.
That's dW dy. But what it really is where it's freaky, is this is negative dW negative dy.
So it's the same exact vorticity despite the fact it's negative.
So
Which
yeah,
makes
so
sense
I have,
because it's the negative
so
over negative.
we originally, I mean, from a perspective of how we were thinking, we said the upward motion increases as I travel north. Here, we would say the downward motion decreases as I go north.
And the signs cancel.
Negatives are still positive.
So in a mathematical standpoint, you're just saying the same thing, but in
But from a
reality,
physical standpoint, I'm seeing it differently. So
Yes.
this is subsidence. So the amount of subsidence is greater, but as I travel to the north, there's less sinking air. And that's a negative vertical velocity. So that's negative W. And then I'm going to the north, it's getting smaller, so it's negative. Or you could say it's the negative velocity. Over here, you'd say the negative or downward velocity is greater as I move south which is negative y. Does that make sense? So there's lots of ways to see vorticity in terms of what's actually happening.
It's kind of cool.
That means it's pretty much all of these statements are true about it at the same time.
Yes, and that's just using your brain. And Allison, this is what I think is the problem, even, you know, like within your students, they're probably so intimidated by the math. They're trying to figure out the math, but the real problem is they're not seeing it what it really is. So their concept is bad. Their math is easy. The concept's the hard part.
Well,
Yeah,
it's
I
connect-
agree.
It's connecting the math with the physical.
Exactly. So just so you know, I'm going to, let's see, stop the share for a second, and I'm going to go to, hold on. Sorry. I'm going to share something, the screen. And I want to go to vorticity equation. I'll go to Wikipedia. And there's just all sorts of things in this one that become difficult. But there is something else I want you to know. And I'm trying to, I'm confused by this because I don't see this often, but I wanted to show you where this is. Okay, so there's vorticity. Notice, what is this Greek letter?
Which one?
This one here. Can you see my cursor?
It's
No.
it's not on the letter.
All right. It's this, it looks like a W, like the top yellow box in your
Oh.
screen.
Delta.
No,
Oh, did I?
what is that letter?
Not delta. What am I talking about? Omega?
That's omega. That's small omega. Okay, so I'm going to do a new share of the whiteboard so I can do this all. I'm going to clear this for a second. And I'm going to show you something that if I have, I don't know what this is. And actually, I'll just do this. And imagine that this is rotating. Okay, so it's rotating.
That's a sphere.
That's a sphere. Okay, so we have a sphere that's rotating. That rotation is omega. So little omega is the rotation. It is a vector because you can curl your fingers, and so the vector points north, up from the North Pole. So here's what you need to know. If this is the Earth, omega is omega, capital Omega. So we use capital Omega for the Earth's basically vorticity. Little omega is for any object rotating. By the way, Well, that's good enough. We'll just talk about that. So does that make sense to you? I just wanted to point that out with you guys.
Okay.
That's kind of a cool little diagram there. Let me share it back to the screen.
Difference between
So that's what they
negative.
say. And then they just give you these terms. Again, now there's commas, which you should know are I, J, K. And then they say something along these lines. Okay, so we're defining, well, here, can you read this out loud? Go ahead, Nick, read that paragraph, would you?
Which one?
Another?
Okay, another important aspect of fluid dynamics that is related to vorticity is circulation. Unlike vorticity, which is a local property defined at every point in the space, circulation is a global property defined by integrating a property of the fluid over a curve. In particular, if you pick any closed contour and denote it with the letter C of t, the circulation around C of t is a counterclockwise direction, is a scalar quantity donated with...
And that's gamma. So what I'm basically saying is this. Look, we know what integration is, right? So let me... you know what? It might be easier if I do this. Integration is from point A to point B of some function of x dx, right? So we're saying I've got some funky function, x, y, or really this is maybe f of x, right? And we're saying if I integrated from point A to point B, what am I measuring? What am I calculating?
The area under the curve.
I'm doing the area under a curve. But what if I have a function, or it's not really a function, but if I have something that's a circle, and I go from A and B are the same point after I go around. Do you understand? I really can't deal with like the value at A and the value at B should be the same. So that's when they come up with this integration. You're integrating around a circuit. You're going in a complete circle. You're ending up where you started. So that is a, what do they call that, a loop function?
No, isn't it a closed interval?
It's called a closed integral.
Interval.
Interval? Isn't it a closed integral?
Yeah, it's a closed integral.
Is it?
I think
Yeah, you're right.
When you
Closed line integral. Okay.
But that should make sense because you couldn't pop A and B if you're going around like a fan. If you're just going in a circle, the value at A and B are the same. So because you're dealing with, you know, the integration of f of x, the antiderivative, I don't even know how you put that, whatever. You're going to evaluate it from A to B, right? But the value at B and the value at A should be the same, so that would always be 0. And we can't say that that's 0 because there is a circulation in it. So what that's telling me is when I go here is I'm integrating U, which is what?
The
Westerly
winds.
zonal wind.
The westerly wind times
Oh, it changes in the north.
Oh, you're ready for an answer?
it's U dx, right? That's what we're looking at. So this is the west wind at a point. And then you're saying, well, how does that west wind change at a point as I move an infinite direction that way? So if something is going in a circle, do you understand as I move in the x direction, I should have a smaller and smaller u wind. So there should be some negative that. And when you add up all those infinite number, right, that's what an integration is, adding up an infinite number. And this is, if you look at the units, this is a meters per second times a meter, because that's meter per second. This is a meter. What do I get?
Meters
Meters
squared per
squared per
second.
second.
Oops. Per second. And if I do it over the entire length, you understand that I would make an area? So I want you to think about this. This is an area per second. So the faster something's moving, the more area it sweeps out inside of the circuit in a given amount of time. But if it's a given amount of time, what is s to the minus 1? If this is area, what is s to the minus 1? What's s to the minus 1?
That's how time is time.
1 over time is?
How it's the
Frequency.
frequency. Duh.
Frequency. So do you agree that something that's creating more area in a shorter amount of time must be rotating faster? So it's the frequency of rotation. So what do you think the unit of omega is?
Hertz.
Hertz per second. So here, go ahead and read this. Nick, you do a good job. Let us take a moment to explain.
Let us take a moment to explain what this is saying physically. At every point on the contour C of t, we find the component of the velocity that is tangent to the curve and multiply this scalar by an infinitesimal length. Projecting the velocity onto the tangent will necessarily give a magnitude between the speed at the position and 0. If the velocity is tangent to the curve, then we get a plus or minus the speed of. If the velocity is orthogonal to the curve, we get 0. Then we integrate this quantity a different way of saying summing an infinite number of things around the contour so that we add the contribution from every point. From this, we ascertain that the circulation along the contour C of t is the amount of flow around the contour C of t, a positive or negative result corresponding to the contour counterclockwise or clockwise circulation respectively.
Contour clockwise, what the hell? Counterclockwise or clockwise?
Okay. One extreme case is where the velocity field is everywhere perpendicular to the curve C of t, and consequently there is no circulation since the flow is always crossing the contour and never flowing along the contour. To get a non-zero circulation, there must be some part of the curve where the flow is along the closed contour. If the velocity is smooth and there are no singularities within C of t, then we use the Stokes integral theorem from vector calculus to rewrite the circulation as
Yeah, and look at this. So what we took, this very simple closed circuit, now we're doing a double integral. A is the area, right? So this is del cross the velocity, that's vorticity, times the n, which is a normal vector to the area. So that's, if you're going around in a circle, that's your thumb pointing up, times the change of the area. So that's how we go to circulations from vorticity. And I'm not going to go into too much of this, but that's kind of where we're going in science. And we're not going to get anywhere near this. But it's pretty cool.
Dang.
Now look at this. Look at this equation. Does this look really hard?
Which one?
This one in the middle. Let me rewrite it. Let me rewrite this one. So it's going to be del rho times del P, or cross, divided by rho squared. Okay, what is del rho?
That's density.
No, del rho is
Pressure gradient?
Density gradient.
Oh, density gradient. Duh.
what is this?
That's the pressure gradient.
Cross product tells me these are both vectors. Remember, gradients? Gradients are vectors that point downhill. So I have a density. Now, instead of density, isn't this a two isobars? Isn't that a pressure gradient?
Yeah.
Mm-hmm.
What is that?
Temperature gradient.
But because at this point here, the temperature is colder than at this there, but it's at the same pressure. So if there's a temperature gradient, which we see in a weather map called isotherms, isn't there a density gradient implied?
So what you're saying is that if we have the pressure and density gradient, there's almost certainly a temperature gradient too.
Yep. And we say it's baroclinic. And baroclinic says we've got temperature advections. I've got temperature gradients. How about this picture? Do you agree there's density here? Less than density there? Do you agree that's a density gradient? A density gradient is going to tell me that air is going to want to go up here, different than this, let's say. And therefore, if I have a circle here, that paddle wheel is going to start to rotate, and that density gradient leads to vorticity. Which means anytime you've got a density gradient, you are generating vorticity. Baroclinic says you've got vorticity. Vorticity means circulations. So go back to here. It says fluid layers of constant density, isopycnal, there's isopycnal is density, want to coincide with fluids of constant rotation. If they do not, in other words, there's gradients, the fluid starts to rotate to make them line up, which causes vorticity to be generated. So I could even think of it this way as going, here's the North Pole, here's the equator. There is a less dense, more dense, and what's the air going to want to do? Shear, density gradient, vorticity, circulation.
Sea breeze.
Or anything.
Yeah.
It's also like the Hadley cell too. It seems to be. Funny how all these circulations end up being the same no matter what they are.
Yeah. But that's how circulation and vorticity are related to each other.
I understand we're probably going to have to put something about circulation into the final project. Is there any specific way or example you think would be better than the rest?
No, I would think, you know, if you want to do a little bit of that integral, maybe go online, do Wikipedia and find some stuff on circulations. Find the stuff that's easy because it can get pretty deep and messy quick. And that's senior and graduate level dynamics. But I just wanted to show you, because what I like to do is teach you the foundations. How do things kind of work?
What does the rho square buy you in the denominator?
Not sure where that rho square comes from.
Why is it squared? Why couldn't it just be rho? It's a scalar.
I don't know. It must come in there when you're multiplying something else.
Never mind.
I don't know offhand. I can't give you. Oh, here. This is what I want. Okay, then we see something like this. Vorticity is a three-dimensional vector. That's given the Greek letter zeta, which is this stupid thing.
Is there a better way to write that?
No, it's dumb. I hate it. To be honest with you, my friend, it's stupid.
I call it a pig's tail.
So it goes like this, right? That's zeta.
So it's like a 5 with a little curly top on it.
So if you see that, that's what it's going to mean. And notice it's going to be del cross V. Now here's an interesting thing. And so let's talk about this. I need to have, in order to have a cross product, I need to have two vectors. So why is it written like this? Why do I have K hat cross del? Or no, dot, sorry. Let's try to draw that better. Why is it this? What this does is it's going to give me a between the k hat and the velocity vector. That will guarantee me horizontal vorticity. Why is it not vertical vorticity? What do you think?
Is the right hand?
Remember, when I cross products, the resultant vector is always perpendicular to the other two vectors.
Vectors.
Right? So if I have a velocity vector, and it might be 3 dimensions, but I cross it by the vertical vector, then I must have a horizontal vector.
What do you do first? Is it left to right? Do the dot product followed by the cross?
I would do, it wouldn't, yes, you have to do this first.
Okay.
And all you're doing is you're creating a horizontal vector. That's all it is. So I want you to look in your book. Page 277. And what they're saying here is they're saying, oops, the Coriolis force, and notice in the book, it's bold C, because a force is a vector. You got to know that. So Coriolis force is a vector. Bold means it's a vector. So I can write it like this, is equal to what? Minus F. By the way, just so you know, F is the Coriolis parameter. So that's 2 omega sine phi. So you probably know that about Coriolis. Times what? K
Cross V.
cross V. So velocity can be an arrow pointing in any direction whatsoever, three-dimensional wind vector. But when I cross it times K, this stays to be horizontal. This is always, the product is always horizontal. So that's their way of doing things like this. Because what's the numeric value of K? Remember, K is a unit vector.
Oh, it's a unit vector. So it's
Means that's the value of 1. So you're not changing anything. You're just focusing on the horizontal vector of it. You take out the cross K and you get a three-dimensional vector, which is fine. But if I want to look at horizontal vorticity, that's what I'm doing. So when you look at that in your book, you will see that that's part of what that is. All right, I need to go here. I'm still not happy because I'm trying to find. Did I just look at? No, I didn't. Yeah, I just looked at that. There is something in vorticity. Bless you.
This.
Sorry, thank you.
Oh gosh, I can't find it because I had found it once in here and it drove me crazy. Does this scare you? This stuff shouldn't scare you. Everything that you do should be taken slowly, telling me about simple things. What is each term telling me? And that's what you do. So, eta, zeta, beta. Oh, maybe I could do that.
There's a good picture.
Yeah, oops. Let me go back here. You want to see that picture?
Bring it in.
Vortex tube. Helmholtz laws. All sorts of cool stuff. It's all derivations from the basic thing. So what I need to do is go vorticity eta, beta, zeta. See if I can find it.
Zeta Phi Beta sorority.
No, I didn't put vorticity in here. Sorry, Allison, if we're boring you here.
No, it's just helping me prepare for grad school.
Yeah, okay. Okay, so over here, take a look at this thing right there. relative vorticity. So that is the total derivative. Sometimes you'll see total derivatives as being capital D. The total derivative of the three-dimensional vorticity with respect to time. Okay? So in other words, how does vorticity in 3 dimensions change with respect to time? Well, one of them is negative v, the zonal velocity times beta, where beta is a change in the Coriolis parameter as you go north. Remember, it's the Coriolis force is 2 omega v sine phi. So as you go north, your sign is changing. That's what's known as the beta effect.
So that's a change in frequency.
Oh.
So vorticity deals with, you get circulations as you spin toward the middle. Okay, so let's see if I can draw this in there. I'm kind of going off field for a little while, but I find it to be interesting. So imagine that I've got the Earth and I'm traveling to the north, and the velocity is fast at the equator, and as I go to the north, the velocity is smaller. Any particle moving to the north will be moving faster than the fluid that it's in. So relative to that, it's going to acquire a drift speed, a zonal velocity. This is just conceptually what's going on. But do you also see that the air starts to curve? And if the air is curving, I'm generating curvature is vorticity. I'm getting a circulation. That's what's known as the beta effect. So what I was trying to explain to you is if vorticity, which is a vector, is 3-dimensional, then I should have a zonal, meridional, and vertical component of this. And I believe that this is beta, this is eta, and this is zeta. So they're saying if you see this little term called eta, sometimes in vorticity, eta is the zonal component of the 3-dimensional vorticity vector, zeta. I think. I might be wrong because I can't find what I want to find. Then you've got the beta term, which I think is right. It's not. And then you've got another term, which they actually use the same letter. So this is going to be bad.
Are those both zeta?
Yes.
Oh.
So I was with Victor and we were talking about stuff. I'm like, what is that letter? Wait, why is this letter here? What is that letter supposed to mean? We were looking at some advanced quotes. And we realized that they use the same letter for a component of vorticity as the entire vector of vorticity. How annoying is that?
Yeah, my dynamics professor does the same thing for regular velocity. He uses U.
And then you start to go, what? And teachers have to realize how bad that is.
But I know kind of as a result of the beta effect, at least in where we are, it's more of something that is going to the northwest, I believe, correct? Because we talked, Ron talked about it in forecasting, which storm was it? I'm trying to remember which hurricane it was. Was that one that was really slow moving though? I don't remember which hurricane that was.
Yeah, okay, so the beta effect denotes how fluid motion is affected by spatial changes of the Coriolis parameter due to the Earth's curvature. The term takes its name from the symbol beta, representing the meridional gradient of the Coriolis parameter at a fixed latitude. You got to admit, there's some cool stuff in here, and it's pretty complicated. So why do hurricanes that form in low latitudes tend to migrate to the northwest? So yesterday I talked about the steering off of tropical cyclones by the mean wind in a steering layer determined by the system's minimal central pressure. For strong hurricanes, the steering layer spans a large portion of the troposphere. Steering layer for a hurricane with a minimal central pressure between 940 and 949 millibars spans from 850 to 250 millibars. The mean wind in that layer is the steering wind, which accounts for 80 to 90% of the hurricane's motion. Wow. Okay. By the way, just so you know, I did not know this. I knew, I would always go, oh, steering winds. And I knew it was some sort of average. I never knew what it actually was. As I mentioned briefly, about 10 to 20% of the storm's motion arises from the beta effect. You might think that forecasting the track of tropical cyclones would thus be child's play, but modeling the beta effect isn't easy. What is the beta effect? For starters, let's agree to restrict our definitions to the Atlantic Ocean and the Northern Hemisphere. The variation of the Coriolis parameter with latitude. The variation of the Coriolis parameter is the primary reasons why hurricanes forming at low levels tends to drift northwestward from their westward track. So you're assuming it's moving from east to west. So before we delve into the nuts and bolts of the beta effect, we need to make sure that all the readers are on the same page. Vorticity is the measure of spin around an axis. For the most part, synoptic meteorology are interested in spin around the local vertical velocity, which is simply a line drawn on a point from the center of the Earth. Blah, blah, blah. We can kind of skip through there. So, by the way, I want to point this out to you so that your notes are better. We have something known as relative vorticity. And I think we've done this in forecasting. Relative vorticity is a result from wind shear, which is what we've done all morning, and curvature. In other words, if there was a pressure gradient and the air was forced to go around the pressure gradient, that's curvature. You're generating vorticity because of this in the curved flow based on the pressure gradient. But there's also something else, which is the Coriolis parameter. Which is 2 omega sine phi. What's omega?
The rotation of the Earth.
Rotational what?
Frequency.
Right? If I use this, that would be the rotational frequency of anything. So if you're on a playground, you would have an omega that will give you a considerably different perspective of the Coriolis force. Okay, sine of the latitude. So understand that this unit of this is per seconds. It is 7.29 times 10 to the minus fifth per second. That is the actual value of the Earth's rotational frequency, which you could solve. Like, how would you know what omega is? How would you know what omega is? The Earth rotates 2 pi radians in 1 day. But how long is a day?
24 hours?
Not really.
Well,
A day is 24 hours, but the rate of rotation is 23 hours, 56 minutes, and I don't know, 8 seconds, something like that. So we say it's a day, but it's really spinning, much faster. Okay. So if you actually did this equation, this is the number you'd come up with, 7.29 times 10 to the minus fifth. So the Coriolis parameter is a sense of rotation. That's the beta effect. There is rotation. So when I take relative vorticity, not humidity, plus F, that gets me something we call absolute vorticity. You guys don't mind when I go off on tangents, do you?
Nope.
I mean, this is the nature of the world around you, and I think it's just more fun when we can do that. It's a small. You guys are a small enough, good enough class that it makes me happy. So I want to show you something. Let's go here. Let's go to the models.
Frequency.
Let's go to the GFS, and we'll go to 500 millibar, and I say vorticity, okay? But what does it say? What kind of vorticity is this?
Absolute.
It's absolute vorticity. And the reason is, if you look at the scale down here, almost all the vorticity is going to be what? Positive.
Positive.
There could be some negative, but almost everything would be positive, because when I look at values of shear and curvature compared to the beta parameter, the beta parameter is dominant. It's big, positive. You would have to have this incredibly strong anticyclonic circulation to end up that the absolute vorticity is actually negative. Almost all the vorticity is going to be positive. So in here, only the grays are negative vorticity. So over here, I probably have some shear zone. I've got very strong winds causing anticyclonic rotation. But when I add it to the Coriolis force, then I get positive vorticity, except for these dark gray areas. So we plot out absolute vorticity, and therefore you can see stuff like this. Just so you know, that's how these maps work. Here's strong positive vorticity with a closed circulation in California. So it may be sheared. So I'm going to lock it in at 45. It may be sheared, but when I look at the wind speeds, I see that, you know, the vorticities would cancel each other out sort of in the middle. But it's pretty cool. Here's your U-wind anomaly. So this is how different are the winds from the west only the zonal component. Down here, I've got 3 sigma, strong westerly anomaly into California. Up here, I've got a negative anomaly of 4 sigma. So I've actually got winds that are from the east, which is going to be way off. I mean, look at this. The winds here are 45 knots from the east. That is highly unusual. Look at the big ridge over us, by the way. Just for the sake of it, I want to take a look at something here. This is actually making me interested. I'm actually getting some rain into California, but not much. Not the valley, but I'm getting some rains into California. Let's take a look at why that is. If I go to my QPF or PWatts, I don't have a big surge of moisture. You see where the deep moisture is? It's out in the middle of the Pacific, and I'm bringing dry air in out of the north. So even though I've got this vorticity center and a big trough, I don't have much moisture with it. I need to start getting these high PWatts into California to get really good rain. And I don't seem to be doing that. There's a little bit as we go way further in time. But I need to see these big PWatts hit into California. Anybody know what that's called? When when you get it from down here and it comes all the way into California?
I didn't quite hear that with the noise.
All right. When you get moisture from down here and it comes into Southern California, you can see the PWATS extending into California.
Mm-hmm.
That's called the atmospheric river. You may hear things like Pineapple Express, but the atmospheric river. Notice what's out here. What is this? 123 hours. It's a big cyclone, right?
Yeah.
I've got a big upper level low that's coming out. Those things are stopping any sort of good flow from coming into Southern California. But that would be true of a La Nina, which is what we're in, which is not necessarily good for California drought ending. Anyway, sorry, I digressed because I got interested in something. Okay, so go ahead and read this for me, Jim. Starting
There are
with
two sources of vorticity that weather forecasters weigh. The first is relative vorticity, which is generated by the curvature of isobars or height contours on a constant pressure surface. For example, an air parcel shaped like a Tylenol capsule acquires relative vorticity as it simply flows through the 500 millibar troughs and ridges. To get your bearings, the contours that form the ridge and trough are 500 millibar height lines. At any rate, air parcels acquire cyclonic vorticity by convention, a positive number, as they round the bend in the trough, and anticyclonic vorticity and negative relative vorticity as they negotiate the curve in the ridge.
that, what we're saying there, that is your trough and your ridge axis. Okay, go ahead, James. Would you read the next one?
Second type.
Yep, horizontal shear.
Second.
No,
Oh,
horizontal.
horizontal. Horizontal. Horizontal wind shear, which is the change in wind speed and/or wind direction over a horizontal distance, is also a source of relative vorticity. In the idealized scenario above, air parcels appear as little fans. The green vectors represent wind. The longer green vectors correspond to faster winds. And so you can get the sense that horizontal wind shear and troughs and ridges cause the fans to rotate, creating cyclonic vorticity in the trough and anticyclonic vorticity in the ridge.
Right, so curvature and shear. Now the second type of vertical vorticity is planetary, which is the spin around a local vertical axis induced by the rotation of the Earth. Note that the vorticity increases with increasing latitude. In other words, if I look down at the North Pole, I have a much higher circulation the further to the north I have. Does that make sense to you? Because
Yep.
I'm traveling
Less distance.
spin, right? The relatively small values of Earth vorticity in the tropics accounts for the reasons why the tropical cyclones must form a minimum of 500 kilometers from the equator, for the most part. Back to the basics of vertical vorticity. I'll sometimes drop the vertical and simply write vorticity. Okay, so what he's telling you here is I should be saying vertical vorticity, thumb pointing up, but he drops that because sometimes people just go vorticity and they're meaning vertical vorticity. Is the sum of relative and Earth vorticity, the Coriolis. That's absolute vorticity. Air parcels moving southward on the western flank of the tropical cyclone center lose Earth vorticity on the west because they're traveling to higher or to lower latitudes. On the eastern side, they gain vorticity. It turns out absolute vorticity associated with hurricanes tends to be conserved in the boundary layer. Thus, the relative vorticity of southbound air parcels must increase on the hurricane's western flank to offset their loss of Earth's vorticity. Since the relative vorticity of northbound parcels must decrease on the eastern flank in order to compensate, as a result, two centers of positive and negative relative vorticity form to the west and east of the hurricane center. Okay, so what that says is this. I have a hurricane. There's your hurricane spinning around. Vorticity gets positive over here and negative over here. That's what it says, right? Positive, negative, relative form the west and east of the hurricane center. Two secondary circulations development, cyclonically around the center and anticyclonically. Do you see now that you have a steering current causing the hurricane to want to move north? You see the vortex here? On the board? Moreover, the beta effect is the reason why tropical cyclones flirting with crossing the equator swerve to the northeast before it's too late. So that's interesting. I'm just reading it to myself. So the beta effect works against crossing the equator. Huh. That's cool. I wish the things were here, but that's pretty cool. That's the beta effect. Okay, so with that said, go ahead and look in your book and look at the things that we're going to need to do. So first thing we're going to talk about is coordinate systems. We've been using X, Y, Z. We have to use S and K. So we're going to talk about that on the next day. But if you look at page 272, we're going to say vorticity and divergence are scalar quantities that can be defined in natural coordinate, but also Cartesian. So what they're saying here is that omega is the rate of spin. That's a scalar. When we make it a vortex, that's when we do the cross product, right? We're getting a vector. So vorticity, zeta, is equal to 2 omega.
Share it, Paul.
I'm reading the book.
Oh, I'm sorry.
I'm reading on page 272.
Oh,
I can probably do this. Oh, okay. All right. So you get the idea of why the Coriolis force is 2 omega? So then there's a talk in here using natural coordinates. And then look at figure 7.2. And the text will talk about this. So here in letter A, we have got pretty much, these are all kinematics, right? We've done this in severe weather. These are all kinematic fields. In letter A, it's not pure zonal kinematics. There's actually going to be shear. Like du dy is going to be some value. At letter B, we've got rotation. At letter C, we've got divergence. At letter D, we have deformation. And we'll talk about those things coming up. But I want you to, now with all the stuff that we've done, I'd like you to study those pages really well for next Tuesday. Okay, that'll take you to 275. So this is really studying. Once we get into the next page, there's a little bit on streamlines versus trajectories. Take a look at that. We'll explain that. And then you can go ahead and read the Coriolis force, which is the next couple of pages as well. And we will derive the Coriolis force very soon. That's gonna.
through
That's gonna.
275.
Yeah, all the way to 278.
Oh, 278. Thank you.
Yeah, and my house should be done by next Tuesday, so I should be in my new office. I'm excited. Allison, you have a good trip. And the rest of you keep doing this studying and then working on that final big project. Okay, because how did you guys get a good headway on that?
Mm-hmm.
Yeah, I think so.
Okay, keep working on it. Remember, you got to be thinking lots of pages. All right, guys, have a great day. We'll see you on Tuesday. Have a good weekend.
Yeah.
All right, you too. Have a good
Take care,
weekend.
Paul. See you
Bye-bye.
on Tuesday.